Okay, so hello everybody. So this is lecture 19 in this course. No, it's not on measurement-based quantum computation, it's on computational models. But this is measurement-based quantum computation, and it's the last lecture on it today. So what we are talking about is the relation of measurement-based quantum computation, entanglement, and the complexity of classical simulation. So so we are asking, when is MBQC efficiently simulable? Simulable is a word that maybe you haven't heard yet. So there was a discussion once whether this should be simulatable or whatever it should be. This basically, when can MBQC be efficiently classically simulated? And we call that simulable. Okay. So there is indeed a bunch of scenarios where you can do that. You've seen one, the one-dimensional case. And then the question is, how far can we push this? And that's what we are going to talk about today, and also what this has to do with entanglement. Let me go to the reading after. So let me say something about the motivation for all of this. So entanglement didn't really occur a lot in this course so far, and probably in many quantum information courses that you have taken, assuming you have taken some, you always hear, oh, entanglement, da-da-da-da-da, most quintessential quantum property. And here, the one thing that you heard about entanglement is too entangled to be useful. Yeah? Okay, and so I want to correct this a little bit. So today's lecture will be about the conventional point of view, where you indeed find entanglement as a precondition for hardness of classical simulation. Yeah? So where entanglement is indeed a good thing, not that there can be too much of it. So today is about the conventional point of view, if you may. Good. So we are relating MBQC with entanglement and classical simulability. So that's the subject of today. There's a bunch of reading about it. So these three papers, they represent a progression of the topic that I outlined on the previous slide. This was the simplest. This is a little better than just talking about the line. This is about trees, when your resource state is a tree graph state. Then you have a significant improvement, but look at these preprint numbers. They are back to back. You see, for one of the authors here, Yayun Shi, outcompeting himself. Good. Yeah. So this is a significant step up, and then the final result is the one down here, due to a kind of fine point that I want to mention, and this fine point has to do with the first paper here on the list. It's graph states and local complementation. So you'll learn about this as we go, but the latter three papers are results on the efficiency of classical simulation of measurement-based quantum computation. And item number 4 is what we will talk about today, and the other two we will only mention briefly. Okay, so further on the motivation of this subject. What we observe is, we can look at the entanglement that is in the remaining resource state as the computation proceeds. Yeah, you measure, and measurement is here in this case, in measurement-based quantum computation, the measurements are all local, and so the entanglement goes down, or at most it remains constant, but it can never go up over time, just because measurement is a local operation. Yeah. So you typically go down in entanglement. So you can think of the entanglement as a resource being spent towards obtaining the computational result. Yeah, and so the limiting case is, well, when you have a product state, there's no entanglement to begin with. So you're not losing any entanglement, but also you really are not computing anything. So that again strengthens this idea that the entanglement in the initial resource state should be the resource for quantum computation. And yeah, so that's a kind of a convenient point of view. And today we want to make it precise. We want to have a result that is really supporting this intuition. Yeah, and that's the result. So this is from a paper by Martin van den Nest, local complementation, the first item on the paper list, also by Martin van den Nest. So in a way, today is Martin van den Nest Day. And here's that central theorem that we want to talk about today and that we want to prove. Oh, well, it's a lot, so I can only sketch the proof. So we consider measurement-based quantum computation on an n-qubit state, specifically a graph state. And that computation is simulable, classically simulable, at a cost that goes linear with the size of the system, but you have this other exponential factor which is dependent on what's called the rank width of a graph, and we'll see what this is. So there is an implicit dependence on the size of the system over here. So the larger n is, the larger the rank width can be. Doesn't need to be, but can be. And so this is really what the hardness of the classical simulation comes from. So this rank width is the complexity parameter of the simulation, but simultaneously it is an entanglement measure. So that is the connection between hardness of classical simulation and entanglement in the state. Yeah? Yeah, so classical simulation is hard only if the entanglement is substantial. So that's the main result that we want to talk about today. Okay, and of course, large part of this is figuring out all these definitions and where this relation comes from. Background and history of the question. So I don't know if I have formally introduced graph states in this lecture. I mean, we had the stabilizer definition for cluster states, that I'm sure, and graph states are basically about the same. Yeah, so for a graph state though, I mean, they are based on any graph. So a cluster state was based on a lattice graph. So here for a graph state, the graph can be anything. There's no regularity required in its structure. It's just some kind of graph, whatever. And so the graph states are stabilizer states. Yeah? So you recall what the stabilizer generators looks like. You pick a site, and then you place a Pauli spin flip sigma x there, and sigma z's on the neighboring particles, neighboring qubits. And neighboring, the neighborhood relation is given to you by the graph. Yeah? So the graph is what tells you who is a neighbor of whom. The graph is where you would apply the Ising interaction if you wanted to create the state from a product state, and so on and so forth. So it's a very modest generalization of cluster states. And cluster states remain special instances of graph states where this graph here is the graph corresponding to some lattice in some dimension. So that is graph states. Okay, so now comes this thing, local complementation. So this has already, backwards, let me maybe begin with this. So this has already been introduced in one of the homework assignments, if you recall. Okay, so these two graph states turn out to be equivalent under local unitaries. So the local unitaries that you would apply to go from here to here, you find here. Yeah, so that is, and okay, and you see the graphs are slightly different. So they can be obtained from one another by a process that's called local complementation. So in this case, local complementation would add that edge. Yeah? And so let's talk about what local complementation is. Okay, so here's another example. It's a little more elaborate, slightly more elaborate, so that we can explain what's going on. So this symbol gamma that appears down here is the adjacency matrix of a graph. Okay, it basically governs the neighborhood relation in a graph. Okay then, so this is our graph here. So we have 4 vertices and also 4 edges. And we now we single out one of those 4 vertices, we call it V here, and now we perform local complementation about this vertex V. So what is happening? So yeah, so you see, something happens to the edges. So there's edges that are new, and there is old edges missing, like here. And also there's old edges remaining. So all the edges that were incident to this special vertex, they have not changed at all. So what has changed is the neighborhood farther away. So what's happening? How is local complementation defined? So local complementation is concerned with the neighborhood of that central vertex that you singled out. And so in this example, the neighboring vertices are those encircled in green. Yeah? These three vertices, they form the neighborhood of this central guy. Yeah? So these are all the vertices that have an edge with the central vertex. And so now the rule, and the physical intuition will come later. So the rule is that the neighborhood, the edges in that neighborhood of the vertex V are being inverted. So this means where there was no edge, you draw one here and here, and where there was an edge, you delete it. So that's what's happening. In the neighborhood, the edges are being inverted. And if you want to write it as a formula, then you come to this. So let's see what this is. So this vector NV is the vector, it has as many components as there are vertices, and a corresponding entry has the value of 1 if you are in the neighborhood, and has the value 0 if you are not in the neighborhood of that vertex. Yes?
Why are the edges to V not inverted?
That's the rule. For now, because V is not in the neighborhood of V. Yeah, so the neighborhood is these three next neighboring vertices.
Only edges between vertices in the neighborhood.
Only in the neighborhood, yeah. Not the edges with the central vertex. So the edges in the edges incident to the central vertex, they are not being affected, and the stuff that's farther away is also not affected. So local complementation is just about the immediate neighborhood. Okay, so here you have this vector again is the index vector for the neighborhood. So it has as many components as there are vertices in the graph, and a component of this vector is 1 if the corresponding vertex is in the neighborhood, and it is 0 if it is not in the neighborhood. Yeah, so it's a vector of zeros and ones. Okay, and so that outer product is a matrix, and that outer product is just added to the adjacency matrix you already have. And the addition is modulo 2. And modulo 2 means inversion. Yeah? So where there was no edge, you add one. Where there was an edge, then you delete it. That's what addition modulo 2 does. Good, so that's the operation. And now, by the way, for some reason that's not so clear to us physicists, the graph theorists already knew that. So that was surprising to Martin van der Nest in quantum information. He came up with it, but the graph theorists already knew it. Yeah, it was interesting. What their motivation was, we don't know. But they already knew it. And that comes up, that will come up a second time in this lecture. Yeah, okay. So the reason why this graph theoretic notion of local complementation is relevant for us is the following. So for any vertex, the graphs G and the one obtained from G by local complementation. So these two graph states related by local complementation, they are local unitarily equivalent. Yeah? So the entanglement structure is completely the same. It's not changed under local complementation. So that's the physical significance of it. And so why am I emphasizing this? So what we are doing in this lecture today, so we are talking about the classical simulation of measurement-based quantum computation. So measurement-based computation proceeds by local measurement. And so now, think of two resource states. One is obtained from the other by local rotation of the qubits, local unitary rotation. So then you can do with the former and with the latter state exactly the same things. The former can simulate the latter by adjusting the measurement basis according to those rotations, or the other way around. They are completely equivalent. So therefore, so what you can do is the same, and also therefore the hardness of the classical simulation of this computation is unchanged under local unitaries. It's an invariant under local unitaries. So now, if your resource state is a graph state, then so certain local unitaries amount to local complementation, and so the actual cost of classical simulation of your computation should be, if your resource state is a graph state, should be invariant under local complementation. Yeah, so the actual cost. So now, when you look at the theorem, so let's go to the theorem statement. Yeah. So here it says, is simulable at cost such and such and such. So this is not the exact value of the computational cost. It's only an upper bound. It can be done at this cost or less. Yeah, but you don't need to spend more. So this is an upper bound. And so now you're asking, okay, so the actual cost is invariant under local complementation. So this does not require the upper bound also be to be invariant under local computation. It's not required. I mean, a bound can be good or bad, but still. I mean, it's a strengthening of the result. It helps you attribute significance to this bound if it is also invariant under local complementation. And that is really what this Van der Nest paper added, the invariance under local complementation. Previous results didn't have it. So that's theorem number 2. Yeah? The graph state of some graph and the graph state of that same graph, but locally complemented about any vertex, these two graph states are local unitary equivalent. So that's theorem 2. And that's kind of a nice exercise in the stabilizer formalism, so we will prove it. Then there is another theorem that we will not prove. You can prove it at home if you like. Theorem 3. So every stabilizer state is local unitary equivalent to some graph state. Yeah? So, I mean, clearly the graph states are special instances of stabilizer states. So the graph state family is contained in the family of stabilizer states. But what this theorem tells you is that essentially that is up to local unitaries, every stabilizer state is a graph state. Yeah? So, I mean, when you're specializing from stabilizer states to graph states, you're not losing much, if anything. Okay, so this is also a theorem, was first proven by Markus Grassel quite some time ago. And you can prove it yourself. You know the stabilizer formalism now, so I will not talk about it here. Let's do the proof of theorem 2. Okay, so we do this a little bit backwards maybe. Let's see where this example was. So in this example, local complementation was about this vertex number 2. And you see, you have a rotation. If you want to go to the graph state with a local complemented graph about that vertex, you have to apply a Clifford rotation about the x-axis on that qubit. And then what that stuff is for, we'll talk about later. Okay, but I want to explain what this rotation does. All right, so what we are looking at here is the stabilizer generator matrix for that graph state. So that's the thing that we begin with. And I hope maybe I would really love to, I would really like it if you had seen that before, but I'm not entirely sure. So the stabilizer generator matrix of a graph state has this very special form where you have just the identity matrix on the left, so that's the X part, and you have the adjacency matrix of that graph on the right. Seen that before? Okay, so let's just do this with an example. So let's do this example. So let's go that route. Then infer the stabilizer generators from it and verify this directly. So let's do this by example. You can, maybe once you've seen the example, you can figure out the general idea by yourself. So we have, the general proof by yourself. Okay, so this is our graph. So tell me, what does the adjacency matrix look like for this graph? Yeah, it's symmetric. Exactly, we're dealing with an undirected graph here. And yeah, this is indeed symmetric. Okay, so then we find that the stabilizer generator matrix looks like this. Yeah, here we have the identity 0, 0, 0, 0. Okay, so this is 2 zeros. And then we have 0, 1, 1, 1, 0, 1, and 1, 1, 0. Okay, just copying that. Okay, so this is our stabilizer generator matrix. So now tell me, without looking at this anymore, so what is the first generator of a stabilizer? Just read it off from this stabilizer generator matrix. Yes? Okay, so let's shorten this up a little bit. So you see, we could have figured this out right away from this description. From the graphical description, yeah? X on some qubit, Z's on the neighbors. Yeah? And with the other two rows, it's exactly the same. Okay, so and now you generalize that. Yeah? So that's why this is the stabilizer generator matrix for graph state. Okay, so we said we were going to do this rotation. We are rotating about rotation angle pi over 2 about the x-axis. So that's that rotation. And we are doing it to qubit V. So what this thing does is, under conjugation, the x rotation takes a z to a y, and a y is an x times a z. So yeah, so what, and the x is preserved. So the x part here is not changed, but here, this entire column, yeah? Stabilizer generator by stabilizer generator, every z becomes a y. And so what this means is, well, it remains a z, but it also becomes an x. And so what that means is, you take this column and add it here. So let's assume this was a proper adjacency matrix. The question came up earlier with nothing on the diagonal, no self loops. So vertices, yeah? So by no self loops, I mean we have no edge of that type. Yeah? So that means the diagonal is empty. Okay, so now when we're adding this column over here, because that element was 0, we had a 1 here, so this remains 1. And then over here off this diagonal element, we're just copying the column. Okay, so that's fine. So that's the stabilizer after. Okay, and so now there's something that we may not like about that so much. We are no longer in graph normal form because we do not have, we have stuff off the diagonal. So next thing we do, let me see if so that stuff we want to get rid of. We want to get back to graph normal form. And so what we do is we remove that stuff by row manipulations. So we are taking this row and adding it wherever we have a 1 here. Yeah? And so tell me, what is the effect of these row manipulations? Yeah? Taking a row from here and adding it somewhere else. What's the physical significance of such an operation? What we are doing, okay, good. So look, so what we just, maybe let me just recap what we did. We were taking a column, and we're adding it over here. So this was column number V in the second block, and we are adding it in column number V on the first block. So that's what we did, and that was the effect of this X rotation on the stabilizer, the X rotation on qubit number V. So that's what that thing did. So moving columns about and adding them and so on and so forth mimics on the stabilizer the effect of a local rotation. Okay, so that is when we operate in columns, and I was now asking you, what is the significance of operating on rows? Yeah, taking a row and adding it somewhere else to another row.
From the Z part.
No, the whole thing. From left to right, whole thing. You're taking an entire row and add it somewhere else. What's that? What's the physical significance of that? Trick alert, but that may be a trick question. That's exactly what it is. We are doing nothing physically. What we are doing is a change of basis. Yeah? So remember, this is a stabilizer generator matrix. It's just a random choice for describing the whole group of stabilizers. Remember, stabilizer is an abelian group, and we have chosen a basis, and when we are adding these rows, then we're just changing the basis. The stabilizer group is unaffected. Yeah? So it's a null operation. Nothing is happening physics-wise. We are still describing the same state, but we are bringing it back to a form that is convenient for us. So we know that we have a 1 here, so we are adding this entire line wherever we have a 1 further up or further down in that column. And in this way, the purpose of doing this is to get back to the identity on the left. That's what we're doing here. So it's another graphic. So we're adding rows. We take this row, add it up here, and so this vector was our incidence, our vector describing the neighborhood, our index vector for the neighborhood. And so horizontal, as was remarked, adjacency matrix is symmetric. So here in this row, we have the index vector transposed. Same information, kind of who is in the neighborhood of that central vertex. And so we take this thing, and since we have taken that part of the row and added it up here, we are also taking that part of the row and adding it up here. Yeah, and we are adding it wherever this index vector has a 1. So that's what we are doing. And the effect of that is that we are adding this matrix. Yeah? So this index vector times its transpose. So that's what we are doing. Okay, so now we have that matrix over there. And so this identity matrix over here. So we are dealing with a graph state. So this is, so we are almost done. And what we have so far been doing is only the X rotation on that vertex V. Okay, but we're not quite done yet with this because remember, we wanted a graph without self-loops. Okay, and a self-loop is a diagonal element of this matrix now. So we want to get rid of the entries 1 in the diagonal where they happen to occur because of this outer product here. Okay, and what do we do physically? So physically, we apply to these qubits to which this happens we apply a z rotation, yeah, pi over 2 z rotation. And so what this does on the stabilizer is, well, first, on the stabilizer, the operation acts by conjugation. And what a z rotation does is it changes a y into an x. So in these locations, because you have the identity matrix over here, so you had a 1 here, a 1 there. So this means you have a y sitting at that location, and now you're doing a z rotation, and this takes this y to an x. Or in other words, this 1 becomes a 0. Yeah? So this is the final step to get it free of self-loops. Okay, is there another slide on that? No, there's not. Okay, good. And so, yeah, so that is the effect of local complementation on graph states. Yeah? So that completes the proof to show that the graph state before and after local complementation are local unitarily equivalent. We have even figured out what the local unitary is. So and there's one item of background material to finish, and that's the Schmidt decomposition. I'm pretty sure you all know this, so I can be super fast. Okay, so here is a pedestrian way of expanding a bipartite quantum state. I'm choosing a fixed basis of states A on the first system and B on the second system, and then I'm just expanding without loss of generality, probably, or with loss of some generality, but probably we would want these to be orthonormal bases. Yeah, and if I'm expanding like that, I'm getting an expansion coefficient with 2 labels, and I'm summing over these 2 labels. I can be more clever. I am adapting the local bases to the states that I'm choosing, yeah, to the state psi, and then I get by with a smaller object. So now it's only a summation over 1 index rather than 2, and also these states have a particular significance. So these states, they are the eigenstates of the respective reduced density matrix. The eigenvalues of the reduced density matrix are these expansion coefficients, absolute value squared. Okay, so that's called the Schmidt decomposition. Yeah? And so that's also going to be important for today, so that this type of decomposition exists for quantum states. And the number of non-zero coefficients you need here has to do with entanglement. Yeah? So if you're dealing with a product state, you have only one non-zero coefficient and you're not entangled. The more such coefficients you have, the more you are entangled. That is covered by the concept of Schmidt rank. The Schmidt rank is the number of the non-zero coefficients that you have, and that is an entanglement measure. It's possible that I was a little bit inconsistent with where I put my logs here. I remove that log. I mean, eventually it has to be there, but we need to make sure that we are not putting it twice. Log gamma is additive under tensoring. I just have to be consistent in where I'm putting the log. If we want to call it an entanglement measure, we probably want to have the log there. And the reason is we want it to be an extensive quantity. Yeah, so if we have a state with respect to a bipartition has a certain amount of entanglement, now we're putting the state twice, and we want the entanglement of the tensor product here to be twice as large, not the former squared. That's why you want to put the log there. To be consistent with the literature, the Schmidt rank is without the log. So that's the quantity. Okay, so this is the log that I was looking for. Okay, so in the rank width formula, we have it consistent with the change that I just made. So I think we are good. All right, good. So let me try to race a little bit. So we are still in this first section on background and history of the subject. Background we have completed. history of the subject. So, one-dimensional case, I mean, we talked about it at length when we explained measurement-based quantum computation. Yeah, so this is your resource cluster state. You measure locally. You want to compute this overlap. And yeah, so we can kind of do this in this half teleportation trick, by this half teleportation trick. Yeah, so this pink bubble, if you write it as a circuit, it looks like this. You have 2 qubits prepared in certain states, entangled, one measured. You know, that's a circuit on the 4-dimensional Hilbert space. It's easy to compute what it does. And it outputs you one quantum state, and that's fed in to the next 2-qubit computation. And so you can move along and along that chain. Okay, so that was the 1D case. We've seen it, was part of the universality proof. So then comes essentially the same one more time. And this is MBQC on graph states of tree graphs. A tree graph is something like this. Yeah, so that's the graph state that we are dealing with now. No loops, trees. Okay, and yeah, it's the same situation. And so what you can do is in time commute or exchange the order of these entangling gates and these measurements. They are commuting operations, so you can exchange them. Okay, and so now you have for now this qubit disentangled from the remainder. And so this is a 1D situation now. You do this as you did before, gets you a new quantum state here, then you do these entangling gates, and that's now a typical 1D situation again. Yeah? So you can move inwards from these ends when you're dealing with the tree graph. So it's basically the exact same story as the one-dimensional situation. So that was the first paper with Yayu and Shi on it. And now comes the other paper of Shi with Igor Markov. And so that's now referring to a situation like this. So this is something that, I mean, this is a graph state corresponding to it, and the graph looks somewhat like a tree graph from a distance, but then it has this fine structure. So it's not exactly a tree, but close to a tree. And the way you describe this closeness to a tree is by a parameter called tree width. And so then Markov and Shi, they have a result like van der Nest, looks pretty much exactly the same, but where their measure, their entanglement measure is the tree width, rather than the width, the rank width that we'll be looking at later. And so that's a very good result. But there's this one thing. Tree width is not invariant under local complementation. So that's kind of the missing bit that van der Nest put in. So here we have 2 graph states, obtained from one another by local complementation. So they have the same entanglement, but this guy has tree width 0 because it is a tree, and this guy has tree width 1. It should be equally hard to simulate, but the tree width upper bound wouldn't show. Okay, and so that gets us to discussing the main results. So that's what this lecture today is about. This theorem that you saw before. Okay, so let's talk about entanglement with measures. And so this is just a lot of space for simple graphics. So we have our resource state psi, and it is a joint quantum state of a bunch of particles. So in this case of 4 particles, 4 qubits. And they are entangled. Now we build this quantum state from its parts. So what we will do here in this case is we will first combine particle 1 and 2, and we will also combine particle 3 and 4. And this gives us the 2 groups. We describe the respective joint systems, and then we join these 2 groups of 2, and this gives us the entire system. Okay, so this is just a kind of conceptual drawing, and we will fill it with substance. So this is what we are looking at. So we are composing our multi-particle quantum state from its parts. So here's another way to write the same situation. So again, we have the 4 particles, and now there is a tree graph associated with that describes just this succession of partitions. So now we've talked about graph states and also graph states on tree graphs. So now here we have tree graphs, but they are a different thing. So we need to tell apart this tree graph structure that deals with the partitionings, and we have to take it apart. Should we describe a graph state down here, which at this point we are not committed to, it can be anything, but in case we do, we have to tell these graphs apart. So this graph is a separate graph, it's just for organizing the partitions. So these vertices down here of degree 1, they are called leaves, and then, well, there is a vertex that's farthest away from the leaves, and it's called root. Yeah, and everything in green here is an internal vertex that has just to do with how we organize writing the state. They have no physical significance. These vertices down here do, so they represent the physical particles. Okay, and so now along these edges we could cut and obtain bipartitions of our system. So this bipartition would give us a 2 versus 2, and this cut would give us a 3 versus 1 partition. We'll come back to that. Okay, so this is just how we are organizing the partitions. And now we are asking a physics question. So given a decomposition tree T, that's the thing we have here, what is the bipartition E that leads to the largest entanglement? Okay, so what has bipartitions to do with edges in this tree graph? So, I mean, that now relates to what was on the previous slide. So if we cut this edge here, we have a bipartition here, and we have a bipartition into a part here and a part over there. So that comes from cutting this edge. So partitions are labeled by edges. We cannot get every partition in this way, but all the partitions that we will need, we can get. And so then we can define an entanglement measure with respect to this tree, and that is the worst entanglement that we get. And so the entanglement measure for now can be anything. So this can be, for example, the entanglement entropy, or it could be log Schmidt rank, anything that works as an entanglement measure. And we're taking the worst edge that gives us the largest amount of entanglement. Yeah? So that we can define as an entanglement measure with respect to a tree. I mean, we can't quite define it. We have to prove something here. What we have to prove for an entanglement measure is that it never increases under local operation and classical communication. So that's a proof you'll find in the fundiness paper and presumably also in the RUG papers. Yeah, so this tree construction has this property. So that's why it is an entanglement measure. And that works for anything for a specific partition, for anything that we're putting in here. Yeah? Think entanglement entropy, think Schmidt rank, log Schmidt rank, anything of those. Yeah, so we are interested in the worst case entanglement that can occur in these partitions, and these partitions depend on the tree that I have chosen. That's a tree that I have chosen. I might have well chosen a different tree. So there would be just another way to organize my partitions. And so what I want is the maximal entanglement, the smallest possible. So I am varying over all these trees that could potentially be used to describe these partitions, and I'm choosing the minimum. For my entanglement, I'm choosing the minimum over all the trees, and the maximum given a tree over the edges. So this min-max construction is characteristic for width measures. Yeah? So there's various types of width measures that are in use, and the way they differ is in what they have here. Yeah, it can be log Schmidt rank, can be a number of things. Okay, but this min-max construction makes it a width. That's the entanglement measure we will be looking at. Okay, so we can, as I just said, we can do this for any measure. But what we will do is we will take it for log of the Schmidt rank. So that will be our measure, and there will be a reason for choosing that measure. And the reason, as we will see in a moment, is that this entanglement measure we can relate to contraction complexity, yeah, to our classical simulation task at hand. Okay, so this is called the Schmidt rank width. Okay, and the Schmidt rank width, different from the Schmidt rank itself, has this logarithm now in it. So it's an extensive quantity, because we are now shifting gears a little bit. We are now moving towards the classical simulation part. Okay, so now we are talking about tensor networks, and they should hopefully look somewhat familiar to you now. I mean, we have definitely looked at matrix product states. I think we have also used the tensor network language. So what is this? So we are describing our resource quantum state that we want to use for MBQC by some tree tensor network, TTN, for tree tensor network. Yeah? So our partitioning tree is back. And so we have now tensors sitting at all the internal vertices, and we have physical states associated with the leaves. And so the state psi, described by this graphical representation, you can also describe by this formula. And so what is this? So you have associated with the leaves states from certain bases. Yeah, and so now you have some expansion coefficient, like you saw it in MPS, but the underlying geometry doesn't have to be aligned now. So the point is, so every index occurs twice. Either you have these internal lines like I and I, so they are contracted, but also sometimes you're contracting, say for the index K here, you're contracting here with here. Yeah, so that's for a line that goes to a physical system. Okay, it's just a contraction of a bunch of stuff. Okay, so I hope that formula is now sufficiently natural for you. So this is the state described by a tensor network. But the state itself is not what we care about. So what we care about are these overlaps. Yeah, for all the local states that can occur in measurement, as post-measurement states, we want to compute these overlaps, and we want to know how hard that is. And so that overlap is also a tensor network, and all that has happened is that these open edges, they have now been replaced by tensors, one-leg tensors that represent the post-measurement states. Yeah, so you have a tensor network in graphical description like that, and as a formula, we had pretty much what we previously had, but instead of the states, local states, we have now these overlaps. So these are just numbers, it's a product of numbers, more numbers, index contraction. So we are just manipulating a large array of numbers. And so the question that now stands, yeah, so this is the physical object of interest. How difficult is it to calculate it? So what is the computational complexity of doing all these tensor contractions, all these summations? Yeah? So that is well, not exactly everything of it, but that is part of the classical simulation question we have to answer. The contraction at a particular vertex interested what's happening here. So that's why. Okay, so what we are doing is we are contracting over these two indices, K and L. Okay, and so, so what, after we've done that, so this tensor with three indices, capital A, small a becomes capital A tilde. And so these edges are now gone, they have been summed over, so this tensor goes from having 3 legs to having only 1 leg. So that's going to be the new tensor, and the question is, how difficult is it to compute that tensor? Okay, so there is summations going on, so maybe we can go back one slide. So this has to do with the tensor A and the indices K and L. So K and L are being summed over. So every such sum, if we run it once, the range of the summation is given by the Schmidt rank. Yeah? So there's the number of coefficients and states and stuff that we have to sum over is the Schmidt rank for that edge. That's one of the summations. Here we are summing over L as well, and the number of summands to add is precisely the Schmidt rank across that edge. Yeah, and then we don't have to do it only once because the resulting tensor has one label of its own I. So for every value that this index can take, we have to do it once. And so the number of values is given by the Schmidt rank with respect to that bipartition, EL. And so the complexity of this is this times this for doing the sum once, for times this for doing it as many times as required. So the contraction complexity is the product of these three Schmidt ranks. So that's the answer. What's the contraction complexity or what the computational complexity? There's footnotes, that's not all there is, but for this one vertex, it is the product of these. Yeah, the product of these ranks. So now remember that we introduced the Schmidt rank width. So 2 to the power Schmidt rank width is, this is the Schmidt rank of the worst bipartition. And so all these Schmidt ranks are as bad as this or smaller. So this is an upper bound for the complexity of the contraction at each vertex. Okay, and so then the question is how many of these contractions we have, and it is n-ish. So how does this come? So we have n indices to begin with, and every contraction reduces the number of remaining indices by 1. So yeah, so that's why n, except for this root vertex, you're reducing the indices by 2. And so it's really rather n minus 1, but never mind. Okay, so that's an upper bound now to the contraction complexity. Yeah, so good. And so the important thing, and that's the statement in the theorem, is that it's linear in n. Yeah, this factor here, polynomial, in fact, third power in 2 to the rank width. Yeah, so it's polynomial in rank width exponentiated. Okay, so that's the contraction complexity. And so what we remember what we should remember for now is that the rank width is simultaneously a measure for the entanglement and for the contraction complexity of this network. So for the hardness of classical simulation by this method. Okay, so that's why it plays that role. Okay, yeah, very nice. But we have been making a few implicit assumptions. Okay, good. Then let's make these assumptions explicit. So I was assuming that we know the optimal tree decomposition T. Yeah, so that was the basis for defining the rank width. How complicated a computation is that? Yeah, so we have to talk about that. And second, I was assuming that we are knowing all these tensors that occur and which bases they refer to. Yeah, so these. Okay, but what justifies this? So this is what we still have to provide. And to sum up these arguments before I go through them, to some extent, this holds if the resource state is a graph state. Yeah, so then these two assumptions are justified. Yeah, so far I have not I mean, in this formula, I have not made that assumption. We will need them here. Okay, so now let's go through these assumptions. Okay, so the assumption was that we know the optimal tree. How come? I mean, we need to get it from somewhere. And fortunately, we can recur to some or refer to some graph theory. But let me back up a little. Let's now specialize. That's kind of for the remainder of the argument, that we specialize to graph states for the resource state. So we know something about the Schmidt rank with respect to any bipartition for graph states. Yeah? And so, okay, so we have the graph state here. We have the graph, and the graph has an adjacency matrix. And so the bipartition means we're also partitioning the adjacency matrix into 2 blocks vertically and 2 blocks horizontally. So overall we have 4 blocks. And so we have the off-diagonal block AB, and then down here we have the transpose, so basically the same thing. And then we have the diagonal blocks. Okay, and so now the Schmidt rank of this graph state with respect to any such bipartition is related to the rank, so the algebraic rank of this adjacency submatrix. Yeah, so this is rank, so all arithmetic here is mod 2. Yeah? Okay, so this is a matrix, it has some rank, and 2 to the power of that rank is the Schmidt rank for graph states. Okay, and so that's now an exercise in stabilizer formalism that you can do at home. I will not do the general proof here, but I will discuss 2 examples. Okay, so that's a formula that I want to at least illustrate. So let's talk about the 1D. Let's talk about the 1D cluster state. Okay, and so if you draw its adjacency matrix, it looks something like this. So you have the diagonal, which is empty. I mean, the main diagonal, which is empty, and then you have the diagonals above and below. Yeah, so they have all ones, both of them. And so you see that one of these diagonals, it just crosses into this gamma AB block with 1 entry. Yeah, so this is your adjacency submatrix gamma AB, and it's all zeros except in its left bottom corner, it has an entry of 1. So what's the rank of that matrix? 1. The rank of that matrix is 1. Okay, and so that fact and that formula up here tells you that the Schmidt rank of that 1D cluster state is 2. Which I guess you knew anyway. Yeah, so that's not new. So then, therefore, if you have two 1D cluster states running in parallel, same bipartition, then the rank of the adjacency matrix would be 2, so Schmidt rank would be 4, and that is exactly as you expected. Let's look at this, in fact, at this double 1D cluster state, but with this additional complication. You have these 2 diagonal edges running. So let's look at the adjacency submatrix gamma AB. So vertex number 1, say this is row 1, is connected to, on the B bipartition, vertices 1 prime, 2 prime. Yeah? Vertex number, oh, excuse me, this is supposed to be 2, not a 2 prime. Okay, vertex number 2 is associated to 1 prime, is neighbors with 1 prime, 2 prime. Da-da. What is the rank? So the rank of that matrix is again 1, yeah, because they are linearly dependent. And so it's 1 and not 2. And so this means the Schmidt rank of this thing is 2 and not 4. Yeah, so the Schmidt rank is the same of what you saw up here. It's not double, or not square of that. Okay? Yeah, so that may be, and that's all due to this little construction. And maybe that is a little bit surprising if you see it the first time. And what does it come from? So maybe in a quantum mechanical way to see that something is different from what you have up there is that you have a stabilizer that lives on the left-hand side that has no counterpart up here. And so look at the stabilizer element. It has an X here and an X there. And then it has Z's, of course, over here. And so this guy would induce Z's here and here, and so would that guy. And so the Z contributions would cancel. And so this means you have an additional stabilizer living exclusively on the left half and also on the right half. And these things, they make the state a little bit more local, hence the reduction of the Schmidt ring. So these things have no counterpart up here. So if you have the stabilizer centered here, goes to both sides. Good, just wanted to say that. Okay, so this is maybe to illustrate that formula in 2 examples. I leave the general proof for you to do. Okay, but why were we talking about it? Okay, we were talking about it because this means that the Schmidt rank width is, same min-max construction as always, is the rank of the adjacency submatrix. Okay, and that is also known as rank width in graph theory. And so for some reason, this graph theorist, Sang-Il PhD thesis Princeton, 2005, he considered this thing. So, and he proved, and that's why we went through this entire exercise. So he proved that if you want to compute this quantity, the optimal tree can be efficiently computed. So this is this other bit of graph theory that was already known before quantum information people could ask for it. And it comes in here very handy. So that takes off item number 1. So the optimal tree can indeed be computed. Good. So item number 1, so the item number 2, was that we get all these coefficients and then the bases to which they refer. And I just want to say that for graph states, all these things are stabilizer states, all these states that occur in the middle, and these coefficients can be efficiently computed. And I leave this for you as a stabilizer exercise, so I will not discuss it here. Okay, and so that was the 2 assumptions that we made and that we still had to clarify. This is now the end of the lecture, and I think I still have 1 or 2 minutes. Okay, so I have the theorem here for you again. So measurement-based quantum computation on an n-qubit graph state is classically simulable at cost, linear in n, but polynomial in the exponential of the rank width of the graph. So the rank width is the essential measure of complexity here in this problem. And so now we understand where these things come from. So poly of this thing, in fact, the third power is an upper bound to a contraction complexity at each vertex in this tree decomposition. There are n vertices in the tree decomposition, so that's this prefactor n. Okay. And so this is where this expression comes from. And so now, final point is that we didn't show it, but this rank width is invariant under local complementation. So that's a property that we wanted to have when we talk about graph states. Okay, so that's the result. So this is the connection between entanglement and hardness of classical simulation of measurement-based quantum computation. So final slide as a concluding remark. So that the connection of graph states to graph theory, is it kind of silly? Is it profound? So at the beginning, we are describing quantum states by graphs, like here. So the graph gives us a stabilizer. So that's some connection, but it doesn't lead you into graph theory proper. It's just a description by a graph. So the graph has vertices and edges, that's all you need. But here, starting with Van den Nest, you're getting deeper into graph theory, namely the notion of local complementation on graphs, was found to be useful for the problem of local unitary equivalence of graph states. And so that's what Funniness figured out. He reinvented local complementation, but was already known to graph theorists. And then comes this other connection with the work of Sangil yeah. So rank width was known to graph theorists really before quantum information people could use it, but found it nonetheless. Okay, so this is funny that these connections exist. Okay, so this is the end of measurement-based quantum computation for this class. Yeah, so there's one proper lecture remaining. That's a lecture tomorrow, so we will talk about the KLM scheme of linear optics quantum computation. And so it has a small graph state part in it, and that's the end. So next week, I think I owe you one lecture more, and this will be a recording, and there will not much will happen in that recording. Tomorrow we'll be done with the material of this class. Yeah, so this will only be kind of a bird's eye view on what we've done. Yeah, we've finished the course material tomorrow,